Section 2-6 and 2-7 notes. We're first going to talk about solving systems of linear inequalities. We show the solution to a system of linear inequalities by graphing them. We've talked about and done graphing of linear inequalities in the past. Let's go over the process again. The process is easier if we put those inequalities into slope-intercept form, y equals mx plus b. Then we graph the lines using the y-intercept and the slope. We make the line dotted if we have a less than or greater than symbol. And we make it solid if we have a less than or equal to or a greater than or equal to symbol. Then we need to shade. Because the solution includes points that are not on the line or are in the shaded area, we need to shade the correct areas above or below the line. We shade above for y greater than or y greater than or equal to, and below if y is less than or y is less than or equal to. So let's look at an example. Here we have a system of linear inequalities. We have two inequalities, 3x plus 4y is greater than negative 4, and x plus 2y is less than 2. Remember, the first thing we want to do is put them in slope-intercept form. Once we've solved for y, then we graph each line. We'll first make a decision about whether we're going to have a dotted or dashed. With A, because it's a greater than symbol, it would be dotted, and we'd shade above. And with B, it would be dotted, but we would shade below. So this is what the graph would look like. Remember that the overlapping shaded area, which you see here in green, is the solution to the system. We also talked about in class how to graph a system of linear inequalities on the graphing calculator. You would simply put those inequalities in as y equals mx plus b in the y equals section of the graph. And then we would go over to the left using the blue arrows to the very left of the y and press enter until it shows the correct shading either above or below. And then we would hit graph, and we should be able to see clearly the overlapping shaded region. And that's your solution. And that within that overlapped shaded region, you will have any point in there fulfill both inequalities. We also discussed in class how you could press second trace, number 5 for intersection, and then choose the two equations and press enter a third time, and we would see the intersection point of those two lines as well. That will help us with our next set of problems. The next process, which is 2-7, also is included in 2-6, but not in word problem form. So it's the same process, just in this case we're going to use word problems. So linear programming. Linear programming is a process of finding a maximum or minimum of a function by using coordinates of the polygon formed by the graph of the constraints. That's a really fancy way of saying that a constraint is a restriction, a boundary, or a limitation. It's really our inequalities. And once we've graphed those and we've shaded the regions, we'll have an overlapped region, which is called a feasible region. It's the area of the graph in which all of the constraints are met. So here's example 1. A farmer has 25 days to plant cotton and soybeans. The cotton can be planted at a rate of 9 acres per day, and the soybeans can be planted at a rate of 12 acres a day. The farmer has 275 acres available. If the profit for soybeans is $18 per acre and the profit for cotton is $25 per acre, how many acres of each crop should be planted to maximize the profits? Well, step number 1, we're going to define the variables. It's obvious by the last question how many acres of each crop should be planted to maximize the profits, what our missing pieces are, or what our unknown values are. C, we could make the number of acres of cotton, and S, the number of acres of soybean. Step 2 is to write the system of linear inequalities. We write these constraints, the limitations given in the problem. Now, obviously, we can't plant less than 0 acres of cotton or soybeans. So our first two inequalities will be C greater than or equal to 0 and S greater than or equal to 0. The next one is kind of obvious as well. The number of acres of cotton planted plus the number of acres of soybean planted has to be less than or equal to what the farmer has to plant on, which is 275 acres that he owns. The last inequality might be the toughest one to build. It's looking at the number of days that he has to plant. If we take the number of acres of cotton that he plants and divide it by 9 acres of cotton per day, that will give us the number of days it took him to plant the cotton. We'll do the same thing with the soybeans. Number of acres of soybeans divided by 12 acres a day gives us the number of days it took him to plant soybeans. We add those together, and that has to be less than or equal to the 25 days that he has to work with. Then we graph these. We discussed in class some different ways of solving these, but we would do the process the way we did with example 1. We would solve for what we have on the y-axis, which is S, and then we'll graph using the y-intercept and slope. We discussed in class one of the equations ends up with a -1 slope. So that would be -1 over 1. Well, because our scale is by 25s in this particular case, we didn't want to go down by 1 and over by 1 because it would be difficult to see on the scale. So we discussed the fact that we could go down by any number as long as we went over by the same number. So we could go, since we start at 0 to 75 for our first line, we could go down 275 and to the right 275 to get another point. So once we've graphed those two equations, we aren't going to actually shade for the first two inequalities, and that's why I've left them out. Really, those two inequalities suggest that we're in the first quadrant, and we don't really need to shade for those. So in this particular case, the purple area is the feasible region. So now we want to name the vertices, those intersection points or the corners of that polygon that's created. So we find the coordinates of the vertices of the feasible region. And here we come up with 0, 275, which was a point I already mentioned, 225, 0, which is along the c-axis, 0, 0, which is an obvious one, and then probably the least obvious is that intersection point of the two lines. You can use your graphing calculator to find that intersection point as discussed previously, or you could use systems of equations. Either way, you come up with 75, 200. Once we know our ordered pairs, then we need to write an equation to be maximized or minimized. Remember that the cost or the profit for planting cotton was $25 per acre, and the profit for soybeans was $18 per acre. So the total profit would be adding those together. This is what we're going to try to maximize. So we're going to build a table to help us to calculate that. We're going to substitute each of the coordinates into the profit equation that we created. You'll see here in the first column the ordered pairs that we found. In the second column, you'll see the equation that we're trying to maximize, or the profit equation, and it shows the calculations. Remember that the ordered pairs represent the number of acres of cotton and the number of acres of soybean. So we put those in the appropriate places and calculate. So our third column shows our profit. And at this point, it's pretty obvious to see which one is the maximum. 225 acres of cotton and 0 acres of soybeans should be planted for a maximum profit of $5,625.